In this video, we're going to consider kind of an unusual problem. Here we have a constant voltage source, and then there's like a network of capacitors. This has 2 farads, 1 farad, a 1 farad capacitor, a 4 farad capacitor, and a 2 farad capacitor. And the voltage source is putting out a current. And this current here is going to get split, obviously. Here we can call this I1. And then there will be a current over here, I2. Like this. And then there will be another current, I3. Like this, and then another one, I4, like this. So it comes here, IS, and it splits into I1 and I2, and then I2 splits into I3 and I4. And we want to know what is the relationship between current I4 and the source current. Now, even though this is a constant voltage supply, the currents that we have in the circuit certainly do not have constant values. They're going to be always changing over time. Remember that even when we have just a very simple circuit with, say, 1 voltage source and 1 resistance, this was the equation that we derived in previous video, or I guess it was number 61, that we can just call this a source current here, or initial value current, and it's going to be decaying exponentially. Then for a discharging capacitor, it's the same current, or the same equation, but with a minus sign because the current is going in the opposite direction. But the point is that even with the simplest type of circuit, that the current is always going to be changing. And certainly, when we have a more complicated one, these currents are not going to be constant in time. Now, the charge across the capacitor, of course, that's this. And as we discussed in the previous 2 videos, the charge that has that relationship, the current is the instantaneous derivative of the charge with respect to time. So the current would be this, and we're going to make use of that in this video. And then from this equation, we can solve for dV just with simple algebra manipulations, and we get this equation. And typically when you see this in textbooks, they'll be talking about integrating from minus infinity up to some point in time t. The point is that when you integrate this, and then you take its limits at minus infinity to t, at minus infinity at 0, so that when you integrate this, you just simply get an expression for the voltage V, and that's this. So in this video, we're going to make use of these 2 equations, remembering that by no means is the current a constant value. It's continuously changing over time. So let's write these down. V equals 1 over C integral of I dt, and I equals C dV dt. And again, if we have an equation that tells us how the current is changing with respect to time, then we can integrate this and we get a specific value for the voltage. Let's start over here at this end, and let's ask ourselves, what would be, say, this voltage here? Call it V4. So that's the voltage across this capacitor. And here then, and here we have the current, that's I4, so we can write a general expression for it, V4 equals 1 over c, that'd be 1/2, the integral of I4 dt. And really that's all we can say about it, because we have no idea what I4 is. We have no equation that tells us how it changes with time. Now what about the voltage at this point, VB? Well, that would equal this voltage plus the voltage across that capacitor, voltage VC. So that equals VBC plus V4. And VBC, again, here we have a capacitor. We know the current going through it. It's I4. And its capacitance is 4 farads. So we can get a general expression for VBC, again, by using this equation. So VBC equals 1 over 4, the integral of I4 dt. So we know what this is, and we have a general expression for V4. So VB, that's this plus this, so we can get a general expression for VB. It'll be 3/4 times this integral. And that's all we can say about it. We have no more specific information. But we know this much. VB, the voltage at this point right here, is not constant. We suspect it's always going to be changing because this is always changing. And if we knew how this changes with time, then we could integrate it. But that would just give us then some expression as to how I4 changes with time. Again, telling us that this is going to change with time. But it's worthwhile to try to get a general expression for the voltage at this point, at point B, because knowing that and knowing what the capacitance is here for this capacitor, we can use this equation to give us a general expression for what the current I3 is. Using this equation, we would have I3 equals C, that's just 1, dV dt. Well, the voltage across this capacitor, of course this is referenced here at ground zero. We know what VB is, we have a general expression for it. So I3 is going to be C, which is 1, dVB dt. And VB is this. So dVB dt, that derivative, that will equal d dt of integral 3/4 times I4 dt. And the derivative of any integral just gives us what's inside the integral, this. So this equals 3/4 times I4. So the derivative of VB is the derivative of this integral. This is what VB is right here. We just derived it. So its derivative is just going to be what's inside the integral, this. But that does give us then a general expression for I3. It equals 1 times this, and this is this. So I3 equals 3/4 of current I4. So whatever I4 is, this current, I3 is going to be 3/4 its value. So here we just derived a relationship then between I3 and I4. What we want is a relationship between IS and I4. So probably we're going to have to keep doing what we've done here in this branch of the circuit and just follow it all the way back. So let's see what happens. So we know that I3 is this. Now what about I2? Well, I2 comes into here, then it splits into I3 and I4. So I2, that's just I3 plus I4. And we have a general relationship now for I3. That's 3/4 I4. We just figured that out. So here we can put in 3/4 I4, and we have that I2 equals 7/4 times I4. So now we have a general relationship between current I2 and I4. So we have a general equation that tells us the relationship between I2 and I4. Eventually we want to know the relationship between this and I4. Now, what can we do at this point? We know this, we don't know it, but we know the relationship between I3 and I4 and I2 and I4. Where can we go from here? We know what this voltage is. We have a general relationship for a general equation for it. It's this. Now, what about this voltage here? Because if we knew what this was, then we could probably get a general expression for I1, just like we did for I3. What we did was, we determined what the voltage VB was right here, then we used this equation, this general equation, to get an equation for I3. So now we should be able to use that same strategy to get an equation for I1 if we can figure out what this voltage is, VA. Well, VA is going to equal this voltage plus this voltage. Or this we call it VB, so it's going to equal VB plus VAB. So let's make some room and write that in. I'm hesitant to erase things because we might need more of this information. Okay, I2 equals 7/4 I4. That we probably want to remember. So, at the risk of being messy, I2 is 7/4 times I4. Okay, let's see if we can continue now. So again, the strategy is this. We have an expression for VB. That's this. And that voltage plus this voltage will be the voltage at A. And it seems like we should be able to determine this voltage here because that's the voltage across this capacitor of 1 farad. Well, we have that, and we have it's a current of I2, so we should be able to use this expression to determine this voltage across the capacitor. That is voltage AB. So add this plus AB, and that will give us the voltage right there at point A. So let's write this down. All we're saying is, it probably sounds more complicated than what it is that VA equals VB plus VAB. That's all we're saying. And we determined that VB equals 3/4 the integral of I dt. We determined that earlier, I4 dt. That we determined earlier. Okay, now what about VAB? That is the voltage across this capacitor that has a current of I2 going through it. So we use this equation. VAB equals 1 over C. That's going to be 1 over 1, so that's just 1. The integral of I2 dt. But I2, we know what that is. That is 7/4 times I4. So we can substitute that in for I2. So it equals 7/4 times I4 dt. So now we can get a general expression for our voltage here, VA. So let's do that. VB, that's this, 3/4 the integral of I4 dt, plus VAB, that's this, 7/4 the integral of I4 dt. So add these together. 7 plus 3 is 10. That's 10/4 the integral of I4 dt. And that is a general expression then for VA. It is this. And again, VA, this voltage right here, that's not a constant value because I4 is always changing in time. And if we knew a specific equation for it, we could determine this specifically. But we don't, so we can't. What we can do is get a general expression for current I1. That's the current going across this capacitor of 2 farads. And we have our general equation is this. So you would have I1 for our specific case. Current I1 will equal C. That's this. That is 2. Times dV dt. Specifically, what is the voltage across this capacitor? It's VA. And VA is this. So I1 equals 2 dVA dt. Or that equals 2. And then we're going to be taking again the derivative of this integral. d dt, the integral of 10/4 or 5/2 I4 dt. And again, when you take the derivative of an integral, it just gives you what's inside the integral, this. So that just simply equals 2 times 5 over 2 times I4. And of course, that's just going to equal 5 times I4. So we have now a relationship between current 1 and I4. That's this. I1 equals 5 times I4. Now, IS, that's split into current I1 and current I2. I1 went down here, and I2 went across here. Well, that's what I2 is. We determined that before, and current I1 is this. So IS equals I1 plus I2. I1, that's 5 times I4. Plus I2, that's 7/4 I4. Or I think this comes out to equal 27 over 4 times I4. So there's our general relationship between the source current and current I4. And that's all. We can't really get any more specific about that because we have no idea of how this changes with time. Obviously, it will be quite complicated because of the nature of our circuit. But that's it. That's all the further we can say. There's nothing more we can do with this circuit. And again, it's kind of an unusual problem, but we thought we would include it because it really gives us a workout here with our concepts. And once we can determine the voltage points at certain points in the circuit, then we get general expressions for the currents at those points in the circuit, again by making use of our equations here. Okay, what we'll do in the next video is we will have capacitor resistance circuits, and we'll have specific values, so it won't be quite such a general open-ended problem as this one was. And I think that the playlist for all the videos, I think this is number 63, the playlist is at the website digital-university.org.